So it's the same basic idea for a t-test as we saw with the z-test, with the normal distribution. We're still finding inference about a population mean. So that hasn't changed. Okay? But as we proceed into like next week and the coming weeks and we have different chapters, we're going to do more with means, compare two means to each other, work with proportions a little bit, and the t-test will help us with that. As I said, our main goal for today is to try to distinguish the differences between the normal distribution, what we have been working with, and this t-distribution. They are admittedly very similar to each other, and that's a good thing. Okay? But this t-distribution helps us kind of overcome some of the limitations that we've already talked about with the normal distribution. So the conditions that we had to use that normal distribution and those z procedures, we needed a simple random sample, and that's always important, right? You don't want a biased data set, you don't want a haphazard data set that's not representative of any population. Okay, so that never changes. Okay, but some of our other conditions, remember we had said that for the normal distribution, we have a normally distributed population, which we verified sometimes, but because of the central limit theorem, we were able to get away with a slightly non-normal population as long as the sample size was big. Because it's the sampling distribution that our procedures reference. The big limitation, though, was this population standard deviation. We just kind of like fooled ourselves around, like saying, yeah, here's our data, okay, and you also happen to know what the population standard deviation is. Okay? That wasn't really practical. And sometimes we kind of got away with just saying, all right, that's ridiculous, let's just use the sample standard deviation instead. Okay? Which is essentially what we're doing today with a couple other changes. Okay? Now, for our inference about a mean, they make a caution here that it's worth noting, but don't worry about it too much. And it says a condition that applies to all of the inference methods in this book or in this course for our sake, the population must be much larger than the sample. Okay, say at least 20 times as large. Okay, so that's not usually something that we have to worry about, but we're using our sample to say something about the population, and we do want that sample size to be pretty large. But the implication there is that the population that this is representing is much larger than that sample. So for example, I mean, you could throw numbers around and practice multiplying by 20. But let's say we had a sample size of 100 people, and you're looking at 20 times as large. So you can get an idea about what that population should be in terms of based off of your sample size. Now, it's previously assumed that we knew this population standard deviation, and therefore we were able to compute probabilities for a sample mean. But in practice, we never know that population standard deviation, okay? Or it would be incredibly like a special case that we would know that. So instead, the logical replacement is to substitute in the sample standard deviation S. Okay? What is the standard deviation of our sample? And that should hopefully be a pretty good representation of what's happening in the population. Because that's the whole goal of what we're doing in the first place. Use a sample to represent the population. Now, our little step size that we've been using so far of sigma over the square root of n, now clearly that needs to change, and it becomes s over the square root of n. And this has a special name that I've already used a little bit. It's called the standard error, or sometimes standard error of the mean, and it's represented SEM. The standard error of the mean is the step size of the sampling distribution. So it's found by that s over square root of n. So you have your distribution shape, the mean is right there at the center. The standard error is how many steps away. What was formerly known as a z-score. Okay, if we had a z-score of 2.5, we're 2.5 standard deviations away. Well, we're getting away from the normal distribution and z-scores. So now we're saying that we are 2.5 standard errors away from the mean. Now, we've spent a lot of time with the normal distribution and this z-score equation. Our value, x bar minus the mean, mu, divided by that sigma over square root of n. So when we're substituting in sample standard deviation for sigma, surprise, surprise, the only real change is that it becomes over s divided by square root of n. We're just replacing in that standard error calculation as part of our t distribution equation. That's a t. That doesn't look like a t. I'm making it worse. And I'm still making it worse. Pretend that says t. Now, because we've made a replacement, how inconsequential it may seem, this new distribution is not normal. Okay? It looks a heck of a lot like a normal distribution, but it's not the normal distribution. Instead, it is a t distribution. Now, there are a lot of similarities between the z distribution or the normal curve and the t distribution. Let me just sketch it out. We have said that the normal distribution is essentially like this. It's symmetric. We have our mean right there at the center. Same thing, very few values on both tails. Now, the t distribution, essentially the same thing, except it gets a little bit taller, or no, not taller, I'm sorry, a little bit shorter because you have more data in the tails. Okay? The tails are a little bit bigger than the normal distribution. We'll explain why. But the similarities, it's still symmetric. It has a single peak at 0, okay, or whatever the mean is. There's much more area in the tails. Now think about frequency distributions as a whole. You have 100% of the data underneath the full curve. So if I'm saying that a t distribution is shorter, and I know you can't see it from my picture here, but if a t distribution is shorter, that area that you're shaving off the top, it has to go somewhere, and it gets spread out into the tails. As opposed to the normal distribution where we know that outliers are very uncommon and they do bad things for the normal distribution. So they are pretty rare. This gets down close to the axis pretty quickly. Okay, so we have more data right around the middle, around the center. We have more variability in a t distribution, meaning that we have more data at the extremes. The t statistic has the same interpretation as any standardized statistic. It says how far away x bar is from any mean mu in standard deviation units. Now, there's a little change with the language here. There's a different t distribution for each sample size specified by its degrees of freedom. Degrees of freedom, I think we saw this term once earlier this year. We see it with a few of our distributions. Essentially, what degrees of freedom are is that if you are a member of that sample, degrees of freedom is how many alternatives are there. Okay? So it's not difficult to calculate. Degrees of freedom for a t distribution is just n minus 1. So if you have 20 people in your sample, there are 19 degrees of freedom. But why degrees of freedom are important is because, like, remember when we were doing the confidence intervals and stuff like that for the normal curve, we had said that, well, a 95% level of confidence is pretty much 2 standard deviations above and 2 standard deviations below. That's because it was the standard normal curve. Okay? It's essentially a single curve, or a single distribution. With a t-distribution, the sample size gives it a new distribution. Okay? It gives it a new height, it gives it more area on the extremes. So we need to use the degrees of freedom to help us get that number of standard deviations above and below when we're creating a confidence interval. We use the degrees of freedom to help us get this t star value. Okay. This gets into, again, degrees of freedom. Okay, you'll see it, df. It's easy to find. You just subtract 1 away from the sample size. And sometimes you'll see it expressed like this. Okay? You have a t-distribution with n minus 1 degrees of freedom. This is not an expression saying t times n minus 1. This is just saying that your model satisfies a t-distribution with n minus 1 degrees of freedom. To find the t statistic, there's no difference between that and z except that sample standard deviation instead of the z, or population standard deviation. So a couple times when we've been doing some things and I just said, well, we don't have the population standard deviation, just put in the sample standard deviation. And we still followed z procedures. And there was some slight inaccuracy with that. But we're doing essentially the right thing. And we were just using a different model for our distribution. Now here's a good comparison chart. It says when comparing the density curves of the standard normal distribution and t-distribution, several facts are apparent. The density curves of the t-distributions are similar in shape to the normal curve. They are symmetric about 0, single peak, bell-shaped, all that stuff. It's the variability that's the key difference. Now, in this picture right here, the purple one, which it gets to be the tallest, is our standard normal curve, based off of population standard deviation. We have 2 different t-distributions here. This red dotted distribution is a t-distribution with 2 degrees of freedom, meaning that there's a sample size of only 3, which gets to be one of our perks a little bit, is that you can get away with smaller samples in a t-distribution, which is a big asset to us, right? We know the bigger the sample size, the better, but sometimes that's not always practical. That's not always feasible. A t-distribution will work with a smaller sample better. Anyway, in this case, you see that that red dotted curve does not get as tall as the normal curve. But on the other end, you can see that there's much more data above the axis down here at the extreme values. There's more variability there. This other one, this bluish-green curve, is a t-distribution with 9 degrees of freedom, so a sample size of 10. And you can see that that gets closer to the normal distribution. Okay? The bigger the sample size, the better, and the more normal it becomes. In theory, if you remember, that sample standard deviation, as the sample size gets bigger and bigger and bigger, it becomes the population. So it becomes the population standard deviation. So you could show this with calculus that if you're to take the limit of a t-distribution, as n approaches infinity, it becomes the normal distribution. So they're essentially the same thing. As the degrees of freedom increase, the t-density curve approaches the normal curve. This happens because S estimates sigma more accurately as the sample size increases, so using S in place of sigma causes little extra variation when the sample is large. Now, we can use a table, okay? Remember z-score chart? We could use that to help us get the z-score, and we looked up a p-value based off of that. Well, we're ditching the normal distribution, so we're ditching that chart. Now, there is a t-chart, a t-table, in the front of your book, okay? This very first page here, this page is the t-distribution. I also have this as a PDF on Canvas. Okay, it's one of the first buttons on that home page. You'll see t-tables, like the z-score table is one of them that you can click. The t-distribution is in that PDF as well. The way this works is you have degrees of freedom down the left side, and across the top you have the confidence interval. Okay, so if I want to be 95% confident, and I have however many degrees of freedom, okay, 11 degrees of freedom. Well, show this chart a little bit differently in terms of the upper tail probability, okay, but that goes along with a 95% confidence interval. You would have that up here as well. This gives you that t-star value of whatever that confidence interval calculation would be. Okay. You go this many standard errors away from the center, away from the mean. But again, it's not going to be the same for every single confidence interval like we saw with the normal distribution. Okay, we could always say sample mean plus or minus 2 of these standard errors, or 1.96, whatever. We round it up to 2. Well, this directly depends on what the sample size is and what the degrees of freedom are to get this. Here is that confidence interval calculation. A one sample t interval for a population mean is similar in both reasoning and computational detail to the one sample z interval for a population proportion. What you're doing is getting your sample mean plus or minus whatever that t star is that you found from the table, where I'll show you technology in just a moment, multiplied by sample standard deviation divided by square root of n. Okay, that's that standard error of the mean calculation. And you're going a little bit below and a little bit above. I will say, back on that previous chart, notice that in this particular case with our 11 degrees of freedom, or a sample size of 12, to get this 95% confidence interval, we were multiplying by 2.201. That's bigger than it was with the normal distribution when it was 1.96, where we rounded it up to 2. That's kind of the sacrifice that we're making in order to get away with a smaller sample and not knowing the population standard deviation. We have a little bit wider, there's more variability in a t-distribution than there is in a normal distribution. Okay? It's the concession that's being made because we don't know those two things. Okay? But it's still a pretty good representation, and the conclusions are still the same. Okay? We're 95% confident that it's between here and here. Yeah, it might be a hair wider than it was before, but it's still precise. We have an example problem here. that we'll use to practice. It says, does the expectation of good weather lead to more generous behavior? Interesting, as our weather gets better and we see highs in the 60s this week. It says psychologists studied this by looking at the size of the tip in a restaurant when a message indicating that the next day's weather would be good was written on the bill. Okay, so kind of giving them the heads up that tomorrow's weather is supposed to be really nice. Enjoy. Does that put people in a good mood and more generous as they are assigning their tip? Well, here are the tips from 20 patrons measured in percent of the total bill. Okay, so we see our values. These are different percentages. Fairly generous tips, it looks like. We want to estimate the mean tip for comparison with tips under the conditions. And so our plan here, we will estimate the mean percentage tip mu for all patrons of this restaurant when they receive a message on their bill indicating the next day's weather will be good by giving a 95% confidence interval. So we do need to start by checking our conditions. It says that this was a randomized comparative experiment, and as a consequence, we are willing to regard these patrons as a simple random sample. All right, so they're randomly obtained. Going ahead here, we need to verify the normality of this. Okay, we can't look at the population of all restaurant tippers. However, we can examine the sample. So you're going to see some of the things we talked about at the very beginning of the year start to come back as quick checks of conditions for us. Okay? We see a stem and leaf plot right here. And by visualizing this stem plot, we can see a single peak right there. I probably messed that up a little bit. There's a single peak. I mean, it's far from being a perfect normal curve. And it's what you get with a sample of 20 individuals. But we're not looking at anything that's like crazy bimodal or anything like that. And remember that it doesn't have to be a perfect normal curve, because the central limit theorem says that this is based off of the sampling distribution. Okay. Now that does have a little bit of a price to pay, because the central limit theorem works when you have a large sample approaching the population, and we're clearly trying to get away with a small sample. So yeah, we know the bigger the sample size, the better, all that stuff. But this is essentially normal. At least not any strong departures from normality. Sample size is at least 15. That's a good rule of thumb for using RT procedures. Okay, so we can proceed with our calculation. Let's take a look at using the calculator in geometry. So I'm going to go back to our screen. Here's our raw data. If you have your calculator with you, let's enter these values in. I have them on my calculator. I'll pull it up here. Anybody want to borrow a calculator? So we're just going to go to list 1 and enter these values, these 20 values, as accurately as possible. So take a minute and do that. Okay, so once we have this data entered, I'm going to switch screens here. So once our data is in the calculator, in our list right there, you can probably figure most of this out. And we're going to go over to our tests menu on the far right. And for the confidence interval, when it was the normal distribution, we were doing number 7, a z interval. Well, go one below it, and you'll see number 8, a t interval. And we'll go with that. Now, once again, you can pull data from the lists under this data tab, or, as some of your textbook problems, you can provide the sample data, sample mean, sample standard deviation, sample size. But for us, let's go with pulling our data from the list, and you can see you don't need to give it anything else. As part of the z interval, you did have to provide the population standard deviation, because in theory, using the z-test, you knew that. A lot of times we were just saying, whatever standard deviation measure we have, we'll put it in. Okay? Now, all you need to do is say 95% confidence. It pulls everything it needs from the list. Just leave that frequency as 1. You're never really going to change that. And then down to calculate. And there's our interval. 21.292 to 23.128. We're 95% confident that the actual mean tip for the people who received this good weather message on their receipt or on their bill is between 21.29% and 23.13%. And it shows you the sample mean, X bar 22.21, and that sample standard deviation 1.96. So pretty easy to do. Let me show you GeoGebra while we're here. Going over to GeoGebra, this has a little bit of a limitation in that yes, you need to pull data from the spreadsheet. Okay, so under the spreadsheet perspective, I entered my data in, and I'm selecting it. Remember, this one variable analysis right here. It gives me the quick histogram, which is a good check of normality. Okay, so that's pretty good for us. But then clicking this number right here, and actually, I'm probably doing more than I need to. Never mind. Click this button for the statistics, and it provides you with the mean and the sample standard deviation here, that 1.96 value that we want. Okay? Now, once you have those, you're going over to that probability calculator perspective. And before we get to that, here is the normal distribution. For a t distribution, it's called the student. And sometimes you'll see that referred to as the student t-test. It's basically like a historical thing where the student wanted to get away with the smaller sample, so it's a student t-test or a student test. And usually we just refer to it as the t-test, but under GeoGebra it's called student. We need to provide degrees of freedom, and then you can play with the boundaries as such. But we want to go under this statistics tab, provide it with the mean, provide it with our sample standard deviation that we obtained from the spreadsheet, or, calculator gave us these same values. We have a sample size of 20, and we pick a t estimate of a mean, and you see our table provides us with not only the mean standard deviation that we just typed in, degrees of freedom, here are our lower and upper boundaries. Okay. So again, this is especially good for when you have a data set that's provided for you. As we get to our homework assignment later this week, remember, some of those homework problems have electronic data sets available that I've linked on Canvas for you, so you can just download them from those spreadsheets, copy and paste them over into GeoGebra, and you can do your analysis that way. You don't need to type in all this stuff on the calculator on every one of those problems. Okay? And I'll link those spreadsheets in the assignment later that we'll be doing later this week on Thursday. Anybody have any questions right now? Okay. I'm not going to show them here, but you can kind of guess that the procedures for the test are the same way. Okay, the t-test of a mean, it's the same kind of thing as a z-test, where you set a null value, provide the mean, sample standard deviation, sample size, and it will come up with a t-score and a p-value. Okay? And we'll talk about that in just a moment here. Same kind of thing with the calculator. So we got this. Again, our interpretation of a confidence interval. We are 95% confident that the mean percentage tip for all patrons of this restaurant is between 21 and 23%. Now, with the one sample t-test, the good news is we've seen the basics. We know what is involved with hypothesis testing. Null and alternative, collect your data, analyze it with a test statistic. The only difference is this time our test statistic is no longer a z-test, it is a t-test. So our equation, the only difference is we're using a sample standard deviation, S, instead of a population standard deviation, sigma. Down here, don't get confused by that. It's just saying the same thing that we saw with the hypotheses before. One-sided or two-sided alternative hypothesis. And it's one-sided if you have greater than or less than, two-sided if you have not equal to. We have a different example problem here for our analysis now. It says the state of Ohio considers it unsafe if a 100 milliliter sample of water in their public parks contains more than 400 coliform bacteria. And I don't exactly know what coliform bacteria is, but they, in the next sentence, describe it as fecal coliform levels. So you can use your imagination there. We have a sample of fecal coliform levels found by laboratories at 20 Ohio State Park swimming areas. Anything over 400, the state of Ohio says is unsafe. We want to know from our sample of 20 state parks, is this good evidence that on average the fecal coliform levels in these swimming areas are unsafe? Well, as a hypothesis test, null hypothesis, we have anything above 400 as being unsafe. So look how they set up their null hypothesis, that the average is 400. Now, that's okay. I did say that we use the equal sign for the null hypothesis. That is true. But I actually introduced this originally as the null hypothesis is always some form of equality. And I think that this would be a good case for us to justify that the null hypothesis should really be mu is less than or equal to 400. Because ideally, you don't want this level of, let's just say it, feces in the public water, in the swimming holes, at 400, which they say is the threshold value for being unsafe. Ideally, you want it less than that. Anything above 400 is unsafe. So that makes sense as our alternative hypothesis that the mean is actually above 400. Reject the null hypothesis that it's safe and accept the alternative that it's unsafe. Now, this kind of comes down to it sounds bizarre, or it sounds difficult, but it's a really straightforward, basic idea of math. It's called the law of trichotomy. Okay, you see that prefix there? Essentially what the law of trichotomy says is that if you are relating two numbers, A and B, they can either be equal to each other, A can be bigger than B, or A can be smaller than B. Those are the only three possible relationships between those two numbers. Okay? I said it was a pretty basic idea. Now with that in mind, in theory, all three cases of this law of trichotomy should be covered by both hypotheses. And we didn't make a big deal about it when we were first learning about hypothesis testing. And it was usually good to just say, well, equals for the null hypothesis, and then if it's one-sided, greater than or less than for the alternative. If it's two-sided, not equal to. But in this case, to satisfy this law of trichotomy and to kind of make sense in the context of this problem, I think our null hypothesis should be that the mean is less than or equal to 400. We have two of the three considered in the null, and we have the one remaining greater than considered in the alternative hypothesis. We have it taken care of. And we're still going by the rule of thumb that the null hypothesis always has some form of equality in it. The null is either going to be less than or equal to, greater than or equal to, or just plain old boring equal to. But in theory, the implication is that if it is a boring old equal to, then you're automatically going with a two-sided alternative hypothesis, and that it could be greater than or less than. If this doesn't make sense, that's okay. You can kind of ignore, I'm going off on a bit of a tangent here. You can kind of ignore this law of trichotomy and just keep using an equal sign in the null and one or two-sided in the alternative. But I want you to kind of think about the implications of what you're saying with that null hypothesis. I think that came to the forefront right here. We don't want 400 as our safe level for public swimming. Ideally, we'd like it to be less than that. So let's say it in the null hypothesis. All right, I'll get off my soapbox. We'll continue on with the problem. Okay. We collected our data. We want to check the conditions, verify normality. Well, we have our histogram right here, and it's not really normal. It's kind of bimodal here. We see a couple of peaks, but it's kind of a good thing, right? Across our sample of 20, at least we have 7 public parks that have something below 500, if 400 is supposedly the maximum safe level. We want as many as we can on this lower end, but we do have several parks that are skewing this data set to the right. Now, that's not the end of the world. Okay? We are willing to regard these particular 20 samples as a simple random sample. The histogram doesn't let us judge normality, but the data are somewhat skewed. Sample size is larger than 15, so it's safe for us to kind of proceed with caution. That's going to become a common phrase for us, proceed with caution. Meaning that, yeah, the conditions are what they are. Like, there's no red flag that we definitely cannot do this. Okay? But we know that we kind of want to be reserved with our conclusions and maybe take it in consideration when setting the alpha level of significance. Okay? So we continue on. We get a sample mean of 1,231.3. When supposedly our maximum safe level was 400. Sample standard deviation of 1037.5. So we could do our one sample t statistic, calculation by hand there. We get a t statistic of 3.5, which still has the same interpretation as a z-score, right? It's not the same p-values that go with it, but we are 3.5 standard errors away from what we'd expect. That's not that common. Okay? So we have 19 degrees of freedom because this is a sample size of 20. So we could use our chart, or more practically, we'll go with technology. Okay? Here's a little refresher about the confidence intervals. What you see, you can do these with the spreadsheet, Excel, or Google Sheets. I would suggest either GeoGebra or the graphing calculator, though, for the t-test itself. Again, same type of procedure that we did for the z-test. On the graphing calculator, we entered this as a one-sided alternative hypothesis. We were worried about the levels being too high. So we set that as greater than our null value of 400. There is our t statistic of 3.58. Our p-value that goes with this, 0.001. Pretty small. The p-value still has the same interpretation. That is the probability of expecting 400 and getting this, getting 1,231 just as chance variation alone. That probability is 0.1%. Very rare. So, our conclusion, reject the null, accept the alternative. We have strong evidence that this mean is actually bigger than 400. Same kind of thing with our analysis from GeoGebra. We get our values on our chart right there, our t statistic and our p-value. Any questions right now? I'm going to pause with that. And what I'd like us to look at for the remaining time is an episode of Against All Odds that talks about what these T procedures are, and again, how they differ from the Z procedures. And they give you a nice little context, a little background story and problem in terms of where the t-test actually came from with their small sample sizes. Okay, so we're going to watch that and let it go from there. I have a few more slides that I'll finish talking about on Wednesday for specifics of the test.